So we'll talk about how to declare functions in Julia. We'll see a few different ways to do that. And then we will talk about duck typing in Julia, mutating versus non-mutating functions, which takes us back to that concept of mutability and why some functions end with an exclamation point. And at the end, we'll talk about higher order functions. And if you don't know what a higher order function is or what mutability is, that's fine. I'll show examples of both of those things to hopefully make them more clear. First off, how to declare a function. So Julia gives us a few different ways to declare functions. The first looks a lot like our syntax for while loops and for loops. We have now our function keyword and always an end statement. Now what we've done here is that we've put the name of the function that we want to declare and parentheses enclosing its input arguments after our function keyword, and then we have our function body on the line or in the lines between the function and the end keywords. So here we're declaring this function called sayHi that's going to greet whatever its input is via string interpolation. And here we have a function f that's going to square its input and return the square. Now, one thing that you might notice here is that we haven't explicitly said what we want either function to return, what we want that return value to be. Now, if we wanted to, we could say return x squared, for example. But we actually don't need to do that because in Julia, by default, whatever's on the very last line of a function will be what gets returned. So having declared sayHi and f in this way, if I call sayHi on the string C3PO, we get a greeting to C3PO. And here we square 42 to get 1764. Now next, another way that we could have declared either of these functions is to do so without using either the function or the end keywords. And we could do that by simply putting the name of the function and that name followed by parentheses enclosing whatever input arguments should go to the function, followed to the right by an equal sign, and then to the right of that, the function body. So this sayHi2 is going to do the same things that the first sayHi function did, and this function called f2 is going to square its input just as the function f did. We can call functions declared in this way, just as we would call functions declared in the first manner. And the final way that we might declare a Julia function is to write them as anonymous functions, also known as the lambda functions. Now, why would we call something a lambda function? The reason that we use the term anonymous function, the reason we use the term anonymous function is because we can actually declare a function without giving the function any name. And we would do that with syntax like I'm showing in this highlighted line here. Having trouble highlighting, but yes. So in this highlighted line, what we see to the left is that we have some input argument, and if we wanted multiple input arguments, we could enclose them as a tuple. But we have an input argument separated from our function body on the right by an arrow that takes us from our input to our output. Now this arrow is created with just a dash and a right pointing arrowhead. So if I run this, I've now generated an anonymous function, and the function being truly anonymous here, I have no way to access the function thereafter. So I can't actually use it, which seems a little silly at first. If you're not familiar with anonymous functions or lambda functions, a very natural question is, why would I ever want a function that doesn't have a name? And I'll show you at the end that you can actually make use of functions that don't have names in particular contexts. But for now, if you like this syntax for generating a function, and you also want to give something a name, you can sort of cheat by assigning a variable to the anonymous function. So here if I say sayHi3 equals the function that I just declared, or f3 equals x to x squared, now I can access either of these functions by calling the variable sayHi3 or the variable f3. And fortunately, the syntax that allows me to actually get at those underlying functions is the same as the syntax for calling the first two ways, or rather functions declared by either of the first two ways above. So now we've seen how to declare some Julia functions. This next section is on duck typing in Julia. If you're not familiar with the expression, if it quacks like a duck, it's a duck, that's where the term duck typing comes from, with the idea being that Julia functions tend to work on whatever inputs make sense. And I'll show you what I mean when I say that. So first off, we have this function called sayHi that we've declared, and we've called it on a couple different strings, where those strings that get passed as inputs to sayHi will get interpolated into an output string that's printed out. Now, we didn't specify at the time of declaring say hi that we wanted it to work on strings, but it worked on strings. And it will similarly just work on numbers. So under the hood, say hi is using string interpolation, and string interpolation will work with numbers just as well as with other strings. So here we're greeting a minor TV character from Peanuts, Schultz's Peanuts. Now similarly, we've seen that the function f works on integers to square them. But similarly, if we had a matrix A, for example, and we call the function f on A, we are going to get a valid output. And the reason is that matrix-matrix multiplication is a well-defined operation in Julia, and that's what gets called under the hood when we try to square a matrix. Similarly, we've seen that the star operator is defined for strings as a way to concatenate them. So if we call this squaring function f on the string hi, we get the output string hi hi. Now on the other hand, this doesn't mean that Julia functions will always work, because sometimes it doesn't make sense and they shouldn't work. An example of that is if we have a vector v, for example. Here this is creating a 3-element vector v. And if we try to call f on v, we're going to get an error. And the reason that we're getting an error here is that vector-vector multiplication is not a well-defined operation. When you try to multiply a vector by a vector, it's not clear if you're trying to take the inner product or the outer product of those vectors, or if you're trying to do element-wise multiplication. So next up is our section on mutating versus non-mutating functions. So when I say mutating functions, I mean functions that will alter the inputs that you've passed to them in the course of calling the function. On the other hand, non-mutating functions will take some input, they'll give you a distinct output, and in the course of running, they will not alter that input that you've given to them. And I'll show you an example of differences in behavior in a second to make that more clear. But for now, in Julia, we have a convention where functions that are mutating are terminated with an exclamation point. Now that is just a convention, so if you write your own function, it will still work with or without an exclamation point if it's mutating or non-mutating. But the convention is there to indicate to you as the user when you should be concerned or aware of the fact that calling a function might update the contents of some of the inputs that you've passed to that function. And you can trust that this convention is followed within the base language of Julia, for example, even though it's not enforced in your own code that you've written. So to look at the difference of a mutating and a non-mutating function, we can look at differences in behavior between the sort function and the sort bang function. So first here I'm creating this vector called v that has 3 input elements, 3, 5, and 2. And if we call sort on this vector v, it gets sorted to show increasing order, elements now 2, 3, and 5. But if we look at v, after calling sort on v, v is still unsorted. It has not been changed by calling sort. On the other hand, if we call sort bang on v, we're going to get, again, the sorted version of the vector v. But if we look at the vector v itself, after calling sort bang, we again have the updated, or rather the sorted version of the vector v. So v itself has now been updated in the course of calling sort bang. And so that's what we mean when we say that sort bang is a mutable or a mutating function. Okay, so our last section in this notebook is on higher order functions. And a higher order function is just some function that will accept other functions as input arguments. Now a classic example of a higher order function, both in Julia and elsewhere, is the concept of a map function. And so what the map function does is that it takes some other function, and what it does with that function is that it applies it to all of the elements of some collection that the function map has access to. So an example of that is here. If we were to call map on the function f, and then the collection, or the vector that contains elements 1, 2, and 3, what map is going to do is it's going to apply the function f to each of the inputs of this collection, and it's going to return an array that has the result of applying that function to each of the elements of the input array inside of it. So here we're squaring the elements 1, 2, and 3 and getting the outputs 1, 4, and 9. I told you earlier that higher order functions, or at least that we're soon going to see a place where anonymous functions without names made sense. And that comes up here when we're talking about higher ordered functions. And the reason is that if we're passing a function to another function as an input argument, as we've done here, passing f to map, that function doesn't actually need to have a name to be useful to us now. So instead I could in place, inside this, as an input argument to map, declare an anonymous function that I want to pass to map. So here I'm declaring this function that takes some input x, cubes the input to return this output x cubed inside my call to map. And there I'm doing element-wise cubing. Now, broadcast is another higher order function in Julia, and it's a lot like map, but it is more general, and so it works in some cases where map does not. For the purpose of this tutorial, we're going to treat broadcast like it's a clone of map, and for example, I'm calling it on f and this vector that contains 1, 2, and 3, and we're getting element-wise squaring. So if we're treating broadcast like a clone of map with a different name, what's interesting about broadcast still is that we have some special syntax for calling broadcast under the hood that allows us to use broadcast without explicitly saying broadcast. And we can do that by simply adding a dot after the name of any function that is in Julia or that we've written ourselves. And this dot is how we access broadcast now. So if I say f dot, parentheses, enclosing my input collection, f gets applied to all the elements of that collection. And to drill that point in home, let's say that we have a matrix A here that's going to have the numbers 1 to 9 from the upper left to the lower right-hand corner. Now if I call f on A to square it, we're getting A times A. On the other hand, if I call f dot A, here we're getting each of the elements of this 3 by 3 matrix squared. And the reason that this dot syntax exists, there are a couple of reasons, but one of the reasons is that it gives you a way to sort of express the math that you might write down in paper in code in a way that's a little bit more natural or closer to the math that you might write down on paper. And so looking at this complex expression with multiple operations going on, it's sort of easier, I think, to look at this expression and have a sense right away of what operations are being performed on which objects, versus in this call to broadcast we have a lambda function declared inside the call to broadcast, and then A passes an input argument, and I believe this is cleaner. Another thing to note about broadcast is that both this dot syntax and the regular call to broadcast will perform exactly the same way. They'll generate similarly performing machine code, if not exactly the same machine code. And other than that, broadcast also does fusion of operations. So it doesn't create temporary variables when moving from the output of one pair of operations going on to another. It sort of does everything in place for you and thereby is more efficient. Okay, so that is it for our whirlwind tour of Julia's syntax.